Now we are going to see another interesting topic. You have it on the board right there, called irrotational flow of an ideal fluid. That means that we are going to look at a pipe as you seeing here, um, and then you're going to have fluid that goes through it, and then we're going to have shaping here that you may say is an obstruction here, or a shape that will allow us to see how the water distribution is done over here, how these contours of different pressures get involved in this inside the pipe. So that's the idea here. So in this, we're gonna call the stream function just the way this stream function would be the way this gets distributed. And we, of course, we want the potential function, meaning the ones that have different pressures. So this is um, flow about a cylindrical body. So let me just disappear from here, and then we will go over here and say, okay, this is the coordinate differential equation. Do you see? It has the same format, but in this case, this is our streamline function, is what we need to draw the contours. Now, interestingly enough, if you have the contours and you take the streamline function and find the gradients, these are vector gradient of a vector. In this case, the gradient of the vector is the is this, which would be the velocity. So the obviously it's pretty clear, we're calculating derivative of a position, so it's no surprise that that's the velocity, right? So what is interesting in this case is that we will see how that velocity gets distributed around that body. See, that's what's important here. And what to do our finite element problem, how to make it work. Do you see here, we start, if we were to do it in pattern, you will start creating a line over here. You will, hold on for a second. I'm going to take color. Here we go. Okay, we will have to define the geometry this way, see? Like this. But I want to show you something here, because if you divide it into these regions like we have in here, how would you do it? You could define it, these points as lines, right? But I want to show you a challenge that you have. This area here, this whole thing like that, is not a finite element, okay? You cannot do it because you have all these lines here. You have all those curves in there. So if you have those curves in here, you need to do small finite elements here. You could do bigger someplace else, but when you have curved surfaces, I'm just letting you know that you need to do smaller elements. But if you're using pattern, then you're gonna have to be careful to define these three regions in there, and then you're going to mesh them separately. Okay, so maybe if I let me make a little drama here, and I am going to maybe put the red region. Yeah, let me do this way. So this guy is the red region. Ah, okay, this is my red region. And now I'm gonna change the pointer color, and then I am going to change this to I'm gonna go and do my green region. Okay, my green region is gonna be like this. So this is my green region in there. And I am going to define yet another region, my blue region. So in here you will have color. I am gonna do the blue region with this blue, okay? And I'm gonna go and build this here like this. I am doing this with a specific intention to develop a skill that you must have in finite elements. Let me pose the challenge for you. This is my blue region, right? This was my green, and this was my red region. Fourth pattern, all those three are different objects. Okay, and if you have to define finite elements that are much smaller on this side, or on the places where you think maybe you need to study, in this case it's fluids, you know, usually stress concentrations are at the corners, but the same idea. You have these three regions, blue, green, and red. How in the world do you make them work together? That's the question here. What I'm trying to illustrate the skill that you must have. Let me do a finite element mesh by hand, and you're gonna see the problem. Okay, let's say that I in here decide that these are gonna be my finite elements. Yeah, I go in here and I mesh this blue region like this. Okay, and let's say I come over here and do it this way. So I have quad elements right in here. Okay, that was the blue. Now what about the green? And I am gonna specify that I would like to have triangular elements on the green region. Now I have thrown a monkey wrench into this, because you're gonna have to figure it out how you transition from this to this. In fact, there is even a bigger challenge than that. Isn't it true that you need to make the boundary elements coincide? And if you don't do it, you're going to end up like this. There is a, let's say you do this. I'm intentionally causing trouble here, guys, because I want to teach you how to get out of this. Because if you're facing this in finite elements, it might not be very nice. Remember, this is a triangular elements. So once we go like this, we could go and do this, right? But the computer is gonna have to do this. See? Okay, and then because the regions are independent, the computer doesn't know that the other one exists. You define 3 areas like this. And what you're doing is something that you don't do with a program like SolidWorks, for example. You're interested in getting the answer, and you don't really care how the computer distributes the mesh. But there are applications like welding, for example, or even this one, that you want one region to have different finite elements than the other. Well, guess what? The computer processes the two separately, and when you don't have this coincidence on this, obviously there is a problem. You may have to remesh this, making sure that the elements over here, I'm gonna draw them, that those guys coincide, because otherwise the transition from one region to the other is messed up. Okay, Patron has a very nice way of doing this, because you need to sew together the blue region with the green, and in the interface, isn't it true that there is a blue node and there's a green node on the same place? Or at least we want it to be that way, because we would like to have a seamless garment parts, seamless garment model. So what do you suggest we do? I have posed the problem to you here. We need to do that, but how in the world are we going to do this? One possibility is to start the mesh on the other side on the same location where the nodes on the blue region end. That's one way, using the mesh seed. But see, this is a bit utopic, because that presumes that all finite elements are the same. And I have been telling you that not all of them are the same. In fact, you don't want them to be the same, particularly in locations where the nodal values are of high interest to you. So now, any ideas? I think the only one that so far we have come up with is that you draw the elements of the other region coinciding with the ones on the prior region. You know, on the red region we could do it, because you see here we already know where the nodes are. Yeah, see? But even if we do that, what I'm trying to illustrate for you is that in here on this boundary like this, you are going to end up with two nodes on the same location. And you do not want that at all. Because if you run it and you persist, Pattern will ignore the second area. Will give you a finite element on the blue maybe, or the green, but not the red. So I have seen this little catastrophe. If you're not prepared for this, this is why I'm giving you this talk. There is a command that before you click on submit the job, because you could do the properties and everything, and the command is called equivalency. So equivalency will throw out. Let me see if I can write it here. This means that the computer is to throw out one of the nodes. Remember one thing, the geometry and the finite elements are separate. But what you're doing is you want that the border of the geometry has common finite elements with the other. And the only way to do this is doing the equivalencing in there, doing it with the computer. Unless you really work hard on making the nodes on one region coincide with the other ones on the other, right? But equivalencing, what it does is erases the superimposed nodes. So if you have nodes on the same location, if you run the equivalencing, it joins everything as one entire region. And it makes it very nice because it solves these geometry problems that we have, let's say the ones on the left, where the nodes on one region do not coincide with the values on the other side, with the nodes on the other. But the one on the red, here on the red side, we pretty much made it all coincide, so everything works fine. Okay, so that's what you gotta do to run the equivalencing, and so that you can actually produce the seamless garment is what I would call it. Okay, so I want you to pay close attention to this solution. This is the solution to the problem I just talked to you about. Do you see the region here? The region, where am I? Right here, this one, region number 1, this number 2, and number 3 over here. All right. Do you see how nicely this is done? This is what I was trying to tell you. You see, you have to make sure that these points work. I think I'm glad we have this color here. So I'm making you see that this sewing it together from area to area, it's extremely crucial for your final element model. And like I say, I repeat, if you're using SolidWorks, this is not an issue. If you're using pattern and perhaps you have composite materials, this is crucial. Okay. Nevertheless, I think since we are in the learning mode, what's important here is to show you the interface, but also take a look at the region that we have just how we did the region around the curve. Hmm? See the region around the curve? Notice here. The elements are small. Same thing here. And look at these ones, they are not even the same. So you want small finite elements in there. So having this and the ability to control the mesh is very important using pattern. This is the answer. Okay, when you run the finite element, these are the piezometric head levels. So this is the object where it was in here, right? Remember? This how the circumference like this. This is the object. And so these are the streamlines that form around the object, see? And what I'm saying, just, needless to say, but just in case, this is 1/4 of it, and here is another part like it, exactly, see? When you use finite elements and doing it symmetrical structures, or for the structures that are symmetrical, you can simplify and use only a part of it. I remember at some point in the past, I looked at the finite element model of the Eiffel Tower. The Eiffel Tower was divided in 8 parts because each one of those was the same, just like we're doing here in 4 parts. Okay, so this, and it will save a lot of computation, because can you imagine how many bars the tower has? And in 3D, with my already presented concept that modeling in 3D requires 6 degrees of freedom per node, and you can't change that. I mean, it's 3D is 3D. So anyway, in here, this would be the streamline. So what I'm showing you here are the solutions. See, this is the solution of the different levels, and this we call it piezometric head 12, 8, 4, 2, and 0 here. But going back to what I was telling you about the contour, I'm gonna make you notice this again. See here? And if we look at this point in here, this point, you see in there? Let's see if I leave enough marks. What I would like to see, leave enough marks in there. Do you realize what I'm saying? That the places where I have the pointer and the one goes out and the other, they're all supposed to be there. See, each one of these, I guess the one computer doesn't like the ones that are too close. The point is, every single one of them, see, is made up of an intersection of 2 sides of the finite element. So that's how you have this. We call it the streamlines, contour lines, or they are piezometric head lines. And that's how we do the simulation solution of finite element models for the finite element models for these fluid mechanic problems.